good morning. Similar to Rebecca, I prepared this very much as quite an informal overview of my work. So apologies if it's not a kind of coherent story, but it's really just a kind of very quick ramble through some of the things I've worked on over my research career. So as a brief kind of history of my work, during my master's, I worked on lattice Boltzmann, which I mentioned just briefly because I know there's some interest within the group. I then moved on to coupled MD simulation. So the idea of this is really to bring molecular detail into a continuum model. So a lot of my early work was actually developing mathematical frameworks that link these two formulations. Some work on constrained dynamics that started to get into kind of physics-y type applications. And then during an EPSRC fellowship, I started to work on molecular turbulence, and I'll talk a bit more about that towards the end. I had a brief stint in Australia in Swinburne, where I worked on heat flux, before moving to chemical engineering, where I started to work on multi-phase flows with surfactants in chemicals. So that's the moving contact line, as well as interfaces between liquids and vapors. I then spent a year in civil engineering, where I worked a bit on granular mechanics, before moving back to mechanical engineering to work on coupled simulation and putting together my software. So I've had a fairly varied journey through pretty much every engineering department. I'm now in aerospace, so I think it's probably just electrical left to do. Okay, so to start with this talk, I'm just going to really explain computational fluid dynamics, just so I can then move on to molecular dynamics and explain the difference between the two. So just to really highlight the inherent assumption that everyone uses when they do continuum fluid dynamics is that we have a continuous field valid at every point in space. So what this actually means is that you can define derivatives, and you can assume these derivatives are valid at any point in space. So you have your mass conservation equations, your energy conservation, and then momentum balance, which is essentially a form of Newton's law in an Eulerian reference frame, which we rewrite with various approximations to get the Navier-Stokes equation. And the case I'm going to talk about today is Coet flow. So usually with counter-sliding walls, so top and bottom, and a typical application of CFD, or and this is direct numerical simulation, is simulating cases with turbulence. But the other application, or the other modelling technique that I want to talk about, is molecular dynamics. And I'm going to focus on this today really just to reassure you or convince you hopefully that it's actually a promising way forward in terms of exploring fluid dynamics. So in this we actually have individual molecules which are discrete and they move around, bear in 1 second. Sorry. Individual molecules, and they move about in continuous space. So you've got individual particles and you're following their position, Ri, as a function of time. So in order to get that position, we basically need the velocities. The velocities come from the accelerations, and the accelerations of those particles essentially just come from Newton's law, F equals ma. So the key difference here from continuum mechanics is we're following individual particles, we're summing up all of their interactions with just other point particles, so nothing in between them. And from that sum of F equals ma, we then calculate the new velocities, then the new positions, and update those. So it's a discrete methodology. But the advantage of this is it's the most fundamental classical methodology. So the only empiricism, the only assumption here is that of electrostatics between the individual particles. So this comes from quantum mechanics, it's an interaction potential of electrostatics, and that gives us our forces. So the reason this is good is because the overall behaviour of just solving F equals ma for lots and lots of molecules is a flow. And this is Coet flow, you've got counter-sliding top and bottom walls. But in doing this, you actually get a whole range of extra physics. So instead of just a no-slip boundary, we have stick-slip near the wall. We get this kind of complicated structure. The overall structure of the fluid itself actually gives you the viscosity. And quite an interesting point is if you look at an individual particle here, if you can see the mouse, an individual particle won't move too far from its given location. So what you actually see is it's the fluid structure itself that gives you viscosity. So by solving this kind of dense fluid, we actually get the viscosity as an output. But the overall behaviour, if you take an average, here we're just basically averaging the velocity in each of these cells, is in agreement with the continuum theory. So the similarity assumption is still valid, even down to these small scales, and overall behaviour matches fluid dynamics, and we get Coet flow analytical solution here. And this is time evolving, and you can show this agrees very, very well, provided you take sufficient statistics. So the advantage is then you can get a whole range of extra physics. So this stick-slip near the wall I show you here is you see a kind of stacking structure in the wall, but you get a liquid-vapor interface, or solid-liquid interface, sorry. And so you can start to build in surface textures. You can look at wall textures. You can also model arbitrarily complex molecules. So this is an example of a biomolecule that you can just download from a database and then start to do fluid dynamics on those molecules. And you can design them to be exactly as complicated as you like. With that in mind, this is some work we did with BP where essentially you have an oil film, water, and you have a shearing force, and you see the film will naturally form over this kind of rough surface. So you can start to explore things like this, building up the molecules using exactly the chemical compositions you know from the manufacturers. You can also model shock waves, and these naturally occur if you apply a large enough force in your molecular system. It's compressible essentially just by the motions through the molecules. You also see naturally formation of droplets. If you have the right temperatures and pressures in your system, it will naturally nucleate. The flip side is it will naturally boil and nucleate and form bubbles at certain points. And then probably the most complicated case is the interface of the liquid, the vapor, the solid, where you have complex chemicals. And this is what I was looking at in chemical engineering. You can actually look at the moving contact line. So this is actually an example where essentially you have the intersection of three kind of failures of assumption in a continuum, and you can actually explore this with a molecular system. So the last thing I want to say about this is actually, if you think about your hierarchy of modeling methodologies, you've got RANS, LES, and DNS modeling the kind of more and more of the turbulent energy. You can think of molecular dynamics as kind of completing this picture down to the actual atomic scale. And the reason I say this is if you actually look at the original paper by Osborne Reynolds, he actually is inspired by kinetic theory to propose the Reynolds stress tensor. And actually from the form of temperature and pressure itself at the molecular scale is essentially just the same quantity. So, you can see this picture where actually these eddies don't just stop at the kind of bottom scale and become like energy by viscosity, they actually continue. So we're not seeing the entire picture, and with molecular dynamics you get energy conservation. So a bit of a hard sell here, but really this just kind of motivates why this is an interesting methodology. So the problem with this, of course, is it's very, very small. We're talking nanoscales, we're talking very, very small simulations. So the idea now is to build this into an engineering simulation that we can apply to industry, we can apply to engineering problems. So broadly speaking, we do the same types of things you do when you do DNS. I mean, no one's doing DNS of a plane. They're using the results from this to tune higher level models. So exactly the same concept here. We'd use a molecular simulation on the left here to build up a table of coefficients, say viscosity or other coefficients of interest. And then we would feed them into a continuum simulation. The next level of complexity in this kind of coupled modelling is to run dynamic simulations as and when you need them. So the idea here is that you run a continuum simulation and you're running a molecular simulation as a kind of reference solution and then feeding that back in, maybe using some form of machine learning. There's been a growth of that recently, but essentially by kind of using these as reference solutions. And then the final form of this is actually to couple the two directly along an interface. And the advantage of this is that near a wall, for example, or near a solid liquid interface or liquid vapor interface, you can model just molecular detail only where it's essential and link it in with the rest. So just give you a few examples from my research of each of these type of kind of coupling and applying this to engineering cases. So I've shown a lot of pretty pictures. This is just to convince you that there's actually some validity to this approach. This is viscosity, surface tension and heat flux. And in each case, the points are MD data, the lines are experimental results. So these are results that are actually coming out of the molecular simulation. So these are not empirical coefficients you have to specify. The molecular dynamics actually predicts these coefficients, which means you can build up molecules and then see what surface tension effects that will have. Try different surfactants and see how the surface tension is affected. Model heat flux within the system. And then you can go beyond this. So I worked in a tribology group, and the idea here is we look at high stresses, high pressures, high shear rates. And what you start to see with this is a whole range of different flow behaviours. So in this example, you can see it becomes solid at high enough pressures. You get plug slip. It's liquid at lower pressures. So you can start to build up a more complicated picture of fluids beyond the continuum. Okay, coming on to the kind of more embedded model. So the idea of this is we actually have a slightly more dynamic, slightly more complicated case. So this is work I did in chemical engineering on moving contact lines. This is a thin film approximation of a moving contact line in an Eulerian reference frame. And the idea is if you think of the moving contact line itself in a kind of moving reference frame, what we're aiming to do is actually model just the very tip using molecular dynamics. So the idea is that we're actually going to feed in just that kind of crucial bit of information that the continuum struggles to capture. And the way I ended up doing this is actually to run essentially correct flow. Most of the cases are correct flow within this talk. But essentially you get a kind of steady state solution, and this allows you to actually explore exactly what happens at the contact line for a range of different velocities, temperatures, and to understand how that would fit in within that. What came of this as well is actually insight into the interface itself. So molecular dynamics, you naturally get the interface, and then the challenge is to understand exactly how that's behaving. So one of the bits of work I did during my PhD is to develop a mathematical framework to essentially write the molecular system in the same form of a control volume as the continuum. So in doing this, we can actually follow the surface, we can get surface tension, we can get curvature, and then you could start to look at things like flow along a surface. So the way to do this is to actually fit a surface using a series of sines and cosines to the kind of intermolecular spacing. And there's a whole range of theory that actually look at exactly how this is valid down to the molecular scale. And then in doing that, we can actually start to get an insight into exactly what's happening at the surface. So one way to think of this is like a Lagrangian reference frame, which actually moves with the fluid surface. So if you had this interface with just a straight reference frame, all you would see is a kind of smeared interface. Whereas if you actually follow the interface itself, you can start to see all of this structure, all of this detail, the fact you've actually got particles naturally forming peaks at different distances from the surface, and then from that you can explore exactly how that affects surface tension, look at putting surfactants in to break that up, etc. And then this is a bit of work I'm doing with Tassos, which is actually on boiling. So the idea here is we're using this idea of if we heat a molecular simulation, naturally we'll see droplet formation or bubble formation. So the heat goes through the lattice here, forms essentially a hotspot that will grow into a bubble. So we see this natural phase change. And so what I've done here is just rendered this as an isosurface of constant density. And what you can see by looking at this is it's actually fairly convincing. You get something that looks quite similar to the continuum, or experiments even, where naturally the bubbles will nucleate at very small sizes, and then various other bubbles will form, they'll coalesce, you'll see a film growing. And essentially you capture these kind of initial onset of nucleation, something that's pretty much impossible to do with a continuum-based model. So then the idea would be that we actually start to put this into a continuum solver. So we embed this in a continuum solver, the actual onset of nucleation, we let that grow, and then once it gets to a certain size, that's passed over to a CFD solver and becomes a bubble that then rises. So, you know, the idea of all of this is really just to kind of capture that key bit of detail you can't get from a continuum model. So the last thing I want to talk about is domain decomposition. So this is really the focus, or was the focus of my PhD. And the idea is we have a link between both, with both MD and CFD having a separate part of the domain themselves. So really this is you know, linking them together with discrete molecules and a continuous field directly as part of the same simulation. So we're writing the CFD in finite volume form. Basically the only thing the CFD sees is the bottom boundary condition. So this bottom boundary condition essentially becomes an average of the molecular region at this point in space. And then to get the two-way coupling, you actually need to apply a force to your molecular system. And this is applied based on the value of the CFD at this cell here. You have a buffer region between the two. And the idea of doing that essentially allows you to do coupling. So it turned out the reason I ended up in civil engineering is because actually this is the same problem as granular mechanics, but with a full overlap between the two. So in this case, you can actually do the forces applied to the particles are directly applied back to the CFD. So conceptually, you can think of this as very similar as particle-fluid interaction inside a substance, but just along an interface. So the software I developed to do this, couple of library, the idea of this was basically you split both into separate codes. You link them through a shared library that just has a kind of initialization, setup, send and receive. So you kind of simplify the problem. And the idea is this for large-scale computation. So to give you some examples of how this works, this is coming back to QEP-flow. The top boundary condition of sliding is in the CFD region here, which are the red crosses. The MD are the green crosses. You have this bottom boundary condition, which is the average of the MD here. This constraint region applied to the MD at the top here. And then the black lines are the analytical solution for QEP-flow. So you can see this kind of coupled case matches very, very well with expected fluid dynamics behavior. But then we can start to explore what happens. Let's say we put in a rough surface. You can see it shifts up the solution. Or posts, for example. Or we can start to have more interesting boundary conditions. So in tribology, they're very interested in polymer coatings. Here, this is a very, very simple example, but you can see it has a pronounced effect on the laminar flow profile here for QEP-flow. And then coming back to our oil and gas example, because the complexity of the oil forms a film near the surface, it means the large part of the simulation we can model using simple Newtonian flow, and all of that complexity is kind of localized to that surface. So we can actually capture that using MD. So the last thing I want to show you is just the molecular simulation of turbulence, and this is something I'm very keen to kind of progress with. It's exactly the same case again, co-ep flow, just much, much bigger. So this goes up to about 300 million molecules. The simulation scale is N, so it's slightly better scaling than CFD, but essentially you're still talking large-scale computations. Still quite small domain sizes. This is actually the minimal channel flow, so Reynolds number 400. And what we see from this, if we're running it, is we actually see the kind of overall breakdown and reformation of streaks. So this is kind of the fundamental mechanism of near-wall turbulence. What's particularly nice about this is it kind of captures all of the complexity of the kind of near-wall structures of turbulence, and by kind of adjusting this, we can actually start to get insights into the kind of underlying mechanism of turbulence. It also happens to be the only case we can do with MD, because it's the lowest Reynolds number. So just to reassure you, at the center line, the two agree. So if you look at the CFD and MD, the two actually have the same velocity. They're actually started from the same initial condition. Because it's kind of chaotic solution, the two will eventually diverge, but essentially you're seeing the same fluid dynamics at the center line. So then the idea is to actually build this in as part of a coupled simulation. So if you look, what you're getting from this molecular near wall region is actually a kind of stacking region near the wall. And then the idea is that the kind of far field and log law region is actually modeled by either DNS, or you can actually approximate using just a kind of similarity approximation. So the idea is that it actually provides greater insight near the wall. So I just want to finish with a simulation here of coupled turbulence, and you can see here the bottom boundary condition to the CFD is actually the near wall region that's actually fed directly from this molecular solver. And so we could start to put in different wall textures and look at how they affect the flow, look at drag reduction by constructing from the kind of chemical species. So that's it for me, just a kind of summary slide of my experience, and I'm happy to take any questions if I haven't overrun.
Any questions? Ed's presentation. I'm going to just kick off myself. So just for my understanding, both CFD and the molecular dynamics are actually defined in the Eulerian framework.
Yes, absolutely. Okay, so yeah, that's a subtlety. So it's in a Lagrangian framework for each individual molecule. So if you think of, from the perspective of a molecule, they're in a Lagrangian framework, you're doing F equals ma. Any averaging you do then becomes in an Eulerian reference frame. So when you want to get fluid dynamics fields from your molecular simulation, you essentially draw a grid on it and you average the velocities, the temperatures, the stresses, or pretty much any quantity you can imagine you can take. But that would then be in an Eulerian reference frame. And then when you come to couple them, you're coupling both in an Eulerian reference frame. Yeah. Please.
Sorry.
What is the exact size that you can simulate to the largest one? I mean, realistically, like you do the water lift, that's going to be very big.
Yes.
But my question is that are you able to catch the two-phase interaction between water phase and an oil phase under a G-force?
Under gravity?
Yeah.
The thing is with gravity, that would essentially be negligible at these scales.
Very big gravity, like 500 G.
Yeah, of course. So if you decided you wanted to, so typically, I mean, similarity seems to work. So the fluid dynamics concept of similarity seems to work. So as long as your non-dimensional numbers are the same, I think that's then reasonable to assume the fluid dynamics should be the same from everything I've seen. So certainly if you were interested in that interface, you would choose certain numbers, I think Grasov numbers or whatever the kind of gravity equivalent that are relevant to that, match those, and then at least you'd get insight into the fluid dynamics. And then what's really nice is then you can start to see exactly what's happening with those kind of interface. And but certainly gravity in its natural form is far too small for these particular simulations. So you would have to do something with similarity solutions.
Just on the, say, the moving contact line with the co-ep flow, so we're looking at a 2D representation. Are you constraining the model to be two-dimensional?
So this is technically three-dimensional. It's just kind of quite shallow in the periodic direction. Yeah, certainly I looked briefly at three-dimensional, and you get a kind of cone, but I was more just interested in using this as a kind of test bed to play around with the moving contact line. For the droplet case, we actually looked at both constrained in 2 dimensions and then a fully 3-dimensional case. And you get some differences, you get some similarities like most of these things, but purely for numerical cases, because we were running lots and lots of these cases to get almost a parameter space. It was just cheaper to do 2D.
Thank you very much.